Hello and welcome to Week 11, Part 5 of EGM310, Image Classification. In this lesson, we will learn about different methods of automated classification, how we can use the computer to help us identify the objects in an image. As we have seen, remotely sensed images can be difficult to interpret. They're usually taken from angles that we don't normally see, and they often have scales that we aren't familiar with. Our goal with remote sensing is to derive information from the raw image data. We want to classify or identify the objects in an image. We might be interested in identifying the burn scars from wildfires, mapping water bodies, or mapping different vegetation types. As you might guess, identifying each and every pixel by hand is an extremely time-consuming task. It can also be physically exhausting, and it's difficult to reproduce. So we normally want to avoid this as much as possible. The process of categorizing raw image data into information that can be used by non-specialists or that can be used as input for further study is what we refer to as classification. The output of a classification routine is a thematic map of the image. You can see here an example of a remotely sensed image on the left, and a thematic map identifying each of the different land cover surfaces present in the image on the right. We're going to be talking about automated classification routines here. That is how we can make the computer do a lot of the work for us. There are a number of different ways that we can characterize different algorithms. We've already seen one of these ways in the second practical. We can do a manual classification, whereby we manually identify every pixel in an image. Or we can do a supervised classification as we did in the second practical. We identify some of the features in an image, and the computer uses that information to determine which of the identified classes each pixel belongs to. In an unsupervised classification, on the other hand, the computer automatically decides how to separate groups of pixels with no input from the user. Classifications can be spatial, where we use spatial information to identify the objects in an image, or we can use the spectral characteristics of the image to identify objects. We can also first group pixels together into objects, then determine how to classify them in what is known as object-oriented classification. Parametric classification methods use some assumption about the statistical distribution of the input data in order to parameterize the input data and somehow interpolate pixel values in order to do the classification. Non-parametric algorithms use some other way of classifying the image based on the input data. Physical models involve modeling physical processes. For example, modeling the interaction of electromagnetic radiation and a surface in order to help identify that surface in an image, whereas empirical models use the properties of the image data to assign real-world properties or categories. We might also think about the fact that many pixels actually cover multiple different surface types. In that case, we assume that the spectral value of each pixel is some combination of defined pure materials, also called end members, that provide a proportion of the pixel value. This is also what is known as a mixed pixel. We can then use this to estimate the fractional area of the pixel that is covered by a given class type. Alternatively, we can assign the class based on the characteristics of the pixel and ignore the potential problem that is posed by these mixed pixels. Finally, hard classifications make a definitive definition about what class each pixel or object belongs to, while fuzzy or soft classifications allow for some level of uncertainty and overlap by estimating the degree of similarity that a given pixel has to each class. Note that these are not mutually exclusive categories. The classification that we did in Practical 2 is a supervised maximum likelihood classification, meaning that it is a supervised classification, but it is also a parametric classification, as the algorithm uses some parameterization of the training data to assign class values to each pixel. In this lesson, we're going to focus on some of the most common distinctions. For example, supervised and unsupervised classification, spectral versus object-oriented classification, and parametric versus non-parametric classification. As we have mentioned in the practical, Unsupervised classification means that we have little to no user input in the classification routine. Instead, the algorithm determines how best to group pixels based on their statistical properties. Common examples of different types of unsupervised classification routines include k-means clustering or isodata clustering, which produce the image shown here. The output classes in this image have no real meaning. They're just grouping based on the statistics of the image data. The user has to actually identify what each of the different spectral classes represents. You have to give the classes meaning in order for them to be useful. Once you've run an unsupervised classification, you can also combine different classes. In the example shown here, in the original unsupervised classification, we can see at least 3 different classes or 3 different colors over the water. This corresponds to the different colors that we can see in the true color image, but because these are all one type of land cover, which is to say water, in the final classification I've combined them into one class. In supervised classification, as we did in the second practical, we train the algorithm using pre-identified areas. These training areas should have uniform characteristics because the larger the spread of pixel values that we include in a training class, the harder it is to have a clean separation between the different classes. We also want them to be spatially distributed throughout the scene as best as possible to help counteract any potential differences in illumination across the image. The computer then uses the data contained within the training samples to determine which class each pixel belongs to, depending on the type of algorithm chosen. Some different examples of algorithm include maximum likelihood, as we used in the second practical, minimum distance, which calculates the geometric center of each of the classes based on the training data. For each pixel, the distance to each class is calculated, and the pixel is assigned to the closest class. In a similar vein, k nearest neighbors takes the k closest training pixels to each individual pixel and assigns that pixel to the majority class. Finally, parallel epiped essentially draws a box around the training classes and assigns all of the pixels that fall within each box to that class. For most of the software packages that do supervised classification, such as ArcMap or Erdos Imagine, you can normally look in the Help menu for more information about the different algorithms available. We'll show how one of these examples, maximum likelihood classification, works. In this example, we have 3 different training classes shown here, with the rest of the pixels in the image displayed as red X's. Using the training data, the algorithm creates a probability distribution function, or PDF, for each class. The PDF is a measure of how likely a given pixel or combination of pixel values is to fall within the given class. So a pixel located here would be more likely to fall within the dark green class. It falls pretty close to the peak of the probability distribution. A pixel here would be more likely to fall within the light green class for the same reason. Note that this approach usually assumes that your training data are normally distributed, that is, that they follow a normal or Gaussian distribution. This is not always the case, and it's something to keep in mind as you're selecting training samples, but also when you're looking at the results. Using this example, we can determine which class a pixel located at the location of this red square should belong to. You can see that it looks like it could belong to either the dark green or the light green classes. You can see that the color level of the probability distribution is the same for each of the 2 classes. It does look like it might be slightly closer to the dark green training pixels, and if we extend a line from the red square up to the probability distribution function, we can see that the probability of a pixel at this location being part of the green class, the dark green class, is just slightly higher. But it's pretty close. This might be an example where we need either more training data to calculate better probability distributions for our training samples, or it might be better to employ a fuzzy classification scheme here. Object-based image classification does a classification based on image objects, not individual pixels. This is somewhat analogous to how we see the world. We see the world as being made up of discrete objects rather than pixels or whatever the equivalent for our eyes would be. The different steps for this are that first, we have to segment the image in order to create discrete objects. Quite often, we do this based on pixel values, grouping nearby pixels together based on their values in different bands or their intensity or some other combination of features. You can see an example of this here. The image objects are all delineated by white lines, so we can see that the islands in the river are all delineated as individual objects. The river itself is also outlined as an object. We have different vegetation types that are included as objects, and we have boundaries between them, and so on. After we've done this, we can do the classification. That is, we take the objects and we give them some meaning to make them useful to extract information. With this approach, we can incorporate spectral properties. For example, the dark green objects are a certain kind of tree, the dark black objects are probably water, and so on. But we can also take into account the shape of the objects. For example, we could differentiate between rivers and lakes by taking into account that a river is most likely going to be long and thin relative to its area, while a lake is normally going to be more compact. We can also use texture. For example, the trees in this image have a very rough texture, as we discussed in the visual interpretation lesson, while the river, even though it has a dark color similar to the trees, looks a lot smoother. Area is another category that we can use to classify image objects. Larger buildings might be industrial or commercial, while smaller buildings are more likely going to be individual houses. We can also include context. We wouldn't expect a white sand beach to be surrounded by agricultural fields, so we can use this relationship to help identify objects or help determine what class that might belong to. Finally, we can use other layers or other data sets, such as elevation, to help us classify objects. We don't just have to rely on the image data. In this lesson, we have discussed how our goal in remote sensing is often to extract meaningful information from raw image data. We want to avoid classifying images by hand. It's normally time-consuming and it can be difficult to reproduce. We discussed how automated classification schemes can be categorized in a number of different ways that are not mutually exclusive. A given algorithm can actually fit into several of the different categories that we talked about. The choice of algorithm we use is going to depend on the input data that we have and the particular application that we have in mind. So once again, you can read more about the concepts that we've covered in this lesson in the textbooks. Chapter 7 of Lillesand, Kiefer, and Chipman, and Chapter 12 of Campbell and Wynn. I've included a link to a video that discusses k-means and image segmentation, as well as an article on image classification in ArcMap. I've uploaded a copy of an article to Blackboard that provides an overview of different classification algorithms. It's a bit long, but you can read it or skim it to find out more about a number of the different types of classification that I've talked about here. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Bye!